All right, today we're talking about Venn diagrams and set operation. This continues my, my love for this particular course so far. Here we are, 3 weeks in, and man, I really like the material of this course. I think this is a lot more fascinating and a lot more useful than college algebra, but just me. So, anyways, let's begin. All right. I don't suppose says too much that we need. All right. So we're talking about Venn diagrams today, obviously, and um, well, it doesn't really give us a breakdown of Venn diagrams before we get into the examples. So we'll just tackle the examples. All right. And this is one in Figure 5. All right. Let's make this a little larger. Guess one of those introduction. Well, let's just read maybe this is an introduction. We can attain a more thorough understanding of sets and their relationship to a universal set by considering diagrams that allow visual analysis. Venn diagrams, named for the British logician John Venn, are used to show the visual representation among sets. So looking at Figure 4, Figure 4 is a Venn diagram. Let's see right here. It's probably not a Venn diagram that you're used to, but it is technically a Venn diagram. The universal set is represented by the region inside a rectangle. So the universal set is this whole big thing, all right, the entire thing. You see the U located here? It is the entire thing. That's the universal set. Typically used, we typically use the variable U to represent the universal set. Pretty clever, right? That's where we at. Subsets within a universal set are depicted by circles, or sometimes by ovals or other shapes. In this Venn diagram, set A is represented by the light blue region inside the circle. Of course, we'll see that here. The dark blue region of Figure 4 represents a set of elements in the universal set U that are not in set A. By combining the regions shown by the light blue shading and the dark blue shading, we obtain the universal set U. So again, which is everything. So let's look at our example here. Example 1 reads, use the Venn diagram of Figure 5 to determine each of the following sets. So for A, we want to find the set of, we want to find, um, the sets of U. Okay, so what all are in U? So looking at our Venn diagram, U is everything, okay, and A is just square and triangle. So U obviously is going to contain a square and triangle, right, because it contains A. So we would say U, well, let's put a big old U there. U is the set, right, so we're going to call it, and we're going to put um, brackets there, and we're going to denote the elements of the set. So the elements of the set are square, triangle. Okay, those are the ones in set A. And then we also have a money sign. Could have positioned this a lot better. I'm sorry. The M and 5. All right, that's the set. That's the set U. B, we want to find the set A. Well, A, as we said a moment ago, simply just contains the elements square and triangle. And then C, the set of elements in U that are not in A. So we'll come up with a word for that here in a moment, but what is in U and not in A? Okay, well, these are all the elements in U, and these are all elements in A. So not square, not triangle. So it looks like just the dollar sign, M, and 5. And of course, we can see that very clearly over here, the dollar sign, M, and 5. So it would be the dollar sign, M, and 5. There is a way to denote the set of elements in U that are not in A, kind of like how we name things, equal sign there. But I don't think we're at that yet, and I'm pretty sure the textbook also doesn't give a proper notation for that as well. Yeah, they don't. So we will skip that for now. Okay, so um, there is something, there's an example going on about uh, donating blood, and it goes all the way to the last example in this section. But we're not gonna deal with that because we're here for the for the big stuff. Uh, so I'm pretty sure like this also this also goes along with the example of donating blood and stuff. But we're going to again kind of skip over that particular portion of this section. So these relationships do talk about it, but I think I can get by with not including it. So figure 8 gets referenced. Does it get referenced? Yeah, figure 7 does. Figure 8. Okay, yeah, we'll just put it. Let's put all these there. Put it right in the middle. Oh, that's not what I wanted. Alrighty, so let's talk about, where's my laser pointer at? We'll talk about dish. Oh, that's not what I wanted. Wrong button. Oh, well, that's never happened. Uh-oh. Uh-oh. Hmm. Okay. So this has never happened because I'd never have made this mistake. So that's not what I wanted. Can we? Okay. You know what? We're going to not mess with that. And we're just going to show the text. All right, so relationships. Relationship 1, disjoint sets. For the record, these notes that, yes, I am providing notes on this particular page, but these notes can be found also in your text under PowerPoint, and they're pretty handy as well. But anyways, relationship 1, disjoint set. So disjoint set. So the word disjoint, even if you don't know the definition of it, you could probably say disjoint are two things that are not the same, right? If something is disjointed, right, it's just like it's not lined up, right? So that's essentially what a disjointed relationship is. There are two sets that they don't have any elements in common. They're disjointed. Relationship 2 is a proper subset. We talked about subsets in the last section. Equal sets, again, kind of pretty common knowledge there. Equal sets, a set is equal to itself if it's exactly itself. And then this is probably what we think of when we think of Venn diagrams. I'm sure you've been exposed to Venn diagrams before, and if you have, this is what you imagine as a Venn diagram, and not necessarily what we saw on the first page. And this is what we're going to be talking about pretty much for the rest of this section, are these kind of Venn diagrams. All right, this is sets with common elements. The light blue on the, because this, again, the universal set is denoted here, is everything. Those elements that are in set A are in this circle, and those elements in set B are in this circle. Right? What's in the middle where the circles overlap are the elements that are in both A and B. And of course, if you have elements strictly over here on the A side, then those are just elements that are in A and not in B. If you have elements over here in the light blue on the B side, we have elements that are in B that are not in A. And as usual, let's go ahead and jump into an example because I feel like that'll make it a lot easier to understand. And this is pretty good too. So let's snip this and we'll give it its own shoot. Go here. We'll snip this and give it its own page. Here we go. All right, things are hopefully back to normal now. But we're going to jump into example 2. And So example 2 reads, use a Venn diagram in figure 12, and let's make it a little bit larger so we can see what is exactly in these particular sets. Hopefully we can fit in some computation here. So A, use a Venn diagram in figure 12 to determine each of the following sets. The universal set. Okay, so the universal set is literally everything, okay? But keep in mind that we're not gonna be including, you know, we're not gonna say A or capital A and capital B, and I'm pretty sure we don't call 1, 2, 3, 4 either, because that is from the previous page. Did it not save? The previous page kind of denoted each individual region. Region 1 being those that are in A that are not in B. Region 3 being those that are in B, not in A. Region 2 being in both A and B. And region 4 being everything. Okay, so that's a tad confusing. So we're going to, for the sake of this example, let's just go ahead and kind of mark out 1, 2, 3, and 4. Okay, again, those are just kind of there to denote um, what each region was from the description before. But anyways, let's move on. So what are the elements in set U? Okay, so again, U is everything. It's the universal set. So I'm just going to list every single thing that we see in this box. U. Okay. And I'm going to have the same issue before. So it looks like A, B, C, D, E, F, G. So just basically A, B, C, D, E, and then we'll put it down here, F, G. Okay. That's A, and then what are the elements in set B? Well, it looks like it's E and D, right? Because if we look, set B is this whole circle here, not just the light blue section there. The light blue section is what's in B and not in A. So it's that entire circle. So it looks like D and E are in B. So we can say the set B, big B, contains the elements D and E. See the set of elements in A but not B. So again, we're looking at here's the elements in A. All right, we're wanting to find the elements in A but not B. Okay, well D is in B, so we're not going to count that. Just A, B, and C are in A but not B, so we'd say A, B, C. Where are we at? C. A. Yes. D is in both. Uh, because this reads the set of elements in A but not in B. It's specifically saying not the elements in B. Mm-hmm. All right, that's C. D. Do you understand? I guess I could have asked before I went on. Okay. Well, we're just basically following along with what it's asking us to do. So D says, or D reads, the set of elements in U that are not in B. So earlier we said U was all of this. Okay. Well, we're wanting the set of elements in U that are not in B. Well, what is in B? Well, D and E are in B. We see here. D and E are in B. So we can pretty much say it's everything but D and E. So A, B, C, F, G. So those are the elements that are in U and are not in B. So A, B, C, not D or E, but F and G. And E, the set of elements in both A and B, and this is the easiest one because there's only one element that's in both A and B, and that would be D. That is the only one that is in both A and B. All right. All right, go ahead. Mm-hmm. That's true. They are. They are all in A. But yeah, D is in B, and we're wanting to find the elements that are in A but not B. Right. All right, the next concept we're going to talk about is the complement. All right, so more new vocabulary, I guess. Some of you might be familiar with the concept of complement, um, but many of you probably are not. Well, you've probably heard of complement, but not this kind of complement. But all complement basically means is we're looking for elements that are not in that particular set. So looking at the definition, put this. Let's make this vertical. All right. So the complement of a set. In arithmetic, we use operations such as addition and multiplication to combine numbers. We now turn to three set operations called complement, intersection, and union. The first one we're going to talk about is complement. The definition of a complement of a set. The complement of a set A. Okay, so we have some set A. The complement is going to be symbolized by A in little parentheses up top. Not parentheses, I'm sorry, comma. Uh, it is a set of all elements in the universal set that are not in A. This idea can be expressed in set builder notation as follows. So A complement is going to be equal to the set of X such that X is in the universal set but not in A. Now here's the thing. I know this probably means nothing to many of you because, well, I mean, just to be honest with you, it's mathematical speak, right? But if we look at this diagram down here, maybe it could help explain it a little bit better. If we go back to our humongous universal set that we talked about earlier, the big rectangle, the big rectangle is the universal set. A complement is everything that is not in A, right? And if we do an example real fast, because I do feel like examples really help out, we'll do example here. Again, all we're looking for is the complement for this particular problem. So this reads, let U equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and A be the set 1, 3, 4, 7. We need to find a complement. So let's write this out a little bit larger so I can cross things off. That's A, or U, and A is the set of odd numbers. 1, 3, 5. My commas there look like periods. 1, 3. No, it's not odd numbers. 4, 7. Okay, so I need to find a complement. A complement is going to be the set that is not in A. Okay, so A has a set 1, so let's cross that off of the universal set. 3, we're going to cross that off the universal set. 4 and 7. So A complement is what is left. A complement is what is not in A. Pretty easy, right? What is not in A? Well, that's 2 is not in A, 5 is not in A, 6 is not in A, 7, I'm sorry, not 7, 8 is not in A, and 9 is not in A. And that's what the complement is. That's the concept of the complement of a set. We just basically write what is not in the set. Right? The next concept we're going to talk about is the intersection. And we talk about the intersection quite often when we talk about sets, intersection and union here in a moment. But the intersection of a set, the intersection of sets A and B written A and then it's an upside down U, right? Stands for intersection, is a set of elements common to both sets A and set B. This definition can be expressed in set builder notation as follows. A upside down U again means intersection. Intersection B is the set X where or such that X is an element of A and X is an element of B. Again, mathematical jargon, but this one I think is a little bit easier to understand than the previous. But again, I feel like examples are what really drive points home. So let's do an example. All right, so the intersection of two sets again um, is are the elements that appear in both sets. So let's do again. Let's rewrite these to make them a little bit larger so I can do some crossing out. So 7, 8. I guess I could just make it super large. Now we'll do this for now because I think later on I'm gonna do something. All right, we will have to scoot this down though. All right, and then intersected with 6, 8, 10, and 12. All right, did I skip something about the empty set? I don't think I did. Okay. Alrighty. So anyways, so we're looking for the intersection of these two sets. They're not named, but this set and that set. We're looking for the intersection of them. Okay, so we're gonna look for elements that are in both. All right. So 7 is 7 in both. I look and know they are not in both. Is 8 in both? Okay, so it looks like I have an 8 here. That's circling in green actually. It looks like I have an 8 here and I have an 8 here. Okay. Now 6, we skipped 6. We went straight to 7. So let's look. Well, 6 is obviously not in both, so we don't have to worry about that. 6, 7, 8. 9 is not in both. 10 is in both. 11 is not in both, but 12 is in both. So the intersection of this particular set, or these two sets rather, we would say is equal to, right? So you would write this big old long thing here, and then you'd write an equal sign off to the right of it, and you would say, well, the intersection is going to be 8, 10. Oh, sorry. There you go. Just simply 8 and 10. Okay. And that's the intersection. The intersection is just the elements that occur in both sets. Okay. Now B, let's not actually write this out. Let's just look at it and do it. So looking at B, we can say, okay, so 1 is not in both, 2 is not in both, 3 is not in both, 4 is not in both, 5 not, okay, so that does not appear to be anything that is in both of these sets. So what's my answer? Okay, well, if they have nothing in common, well then we say that the empty set is is the thing they have in common. They both contain an empty set. And if you recall from sets in the previous sections, the empty set is a subset of every set. So that is indeed what they have in common. And then C, we have the empty set and 1, 3, 5, 7, 9. Okay, the intersection of the empty set and 1, 3, 5, 7, 9, same answer is going to be the empty set. Okay, because again, the empty set is a subset of every set. It's not necessarily written in every single set, but like for instance, this set does indeed include the empty set. This does include the empty set. The empty set is just an implied subset of every set. And again, we saw that in the previous section regarding sets. All right, the last concept is going to be the union of sets. The union of sets is going to be the easiest, I think, the easiest concept, because it's just basically every single element that you see in the two sets. Alrighty. So again, let's actually read the definition. The definition is, gotta get my laser pointer up here. The definition, the union of a set A and B written A, and then this time we have an actual right side up U, right? And it stands for union. A union B is a set of elements that are members of set A or of set B or of both. The definition can be expressed in set builder notation as A union B is equal to the set X such that X is in A or X is in B. So it's just basically listing off everything. We don't skip an element. We don't repeat an element. We just list them all off. So A, it looks like 6, 7, 8, 9, 10, 11, 12. So that is the set 6, 7, 8, 9, 10, 11, and 12. Again, we just wrote everything there. That is the union of that set of those two sets. B, it looks like 1, 2, 3, 4, 5, 6, 7, and it looks like just 1 through 9 this time. Just writing every single element that I see. There's no crossing off. What did I say? 1, 2, 1, 2, 3, 4, 5, 9. There's no crossing off. There's no computation. It's just write everything. And then C, 1, 3, 5, 7, 9, union with the empty set. And again, the empty set is part of every set. So we're basically just rewriting the first set here. 1, 3, 5, 5, 7, 9. Okay. Oh, I knew we talked about the empty set at some point. I guess we'll just put this onto this current page. Of course, we talked about it already, so I guess it's not necessarily new. But I did say that well, I guess the intersection could be kind of a new concept. So down here, the empty set and intersection and union. So A intersected with the empty set is going to be the empty set, okay? Because again, every set contains an empty set, and the empty set only contains the empty set. So obviously the intersection of them will be the empty set. And 2, A union with the empty set. Of course, we saw that with example 5C here. A union with the empty set is just going to simply be A. And of course, this set union with the empty set was just this set. And of course, we wrote that over here. I think next time I teach this, I'll put that definition first. Okay. So performing set operation is on sets is well, kind of like how you would imagine, right? We remember PEMDAS. It's kind of like PEMDAS, right? We're going to deal with the things that are in parentheses before we deal with anything else. So, performing set operations, some problems involve more than one set operation. The set notation specifies the order in which we perform these operations, right? The set notation, of course, means we're going with PEMDAS, right? Always begin by performing any operations in parentheses. Here are two examples involving sets. We will find example 6. Of course, we'll just do example 6, but we're going to do everything that's done in parentheses first. Okay, so for instance, finding A union B, the complement of A union B, well, we're going to find A union B, and then we're going to do the complement. In this particular example, we're going to find the complement of both A and then B, and then find the intersection. And of course, I guess that's what we're doing here. And I think this is where I wanted to okay, so let's actually let's change gears just a tad because I want to have a lot more space to write these sets. So let's actually give the performing sets, we're going to give it its own page. And then we'll do example 6. Okay, so I had an idea to do this, and let's just see if we can get this to work. Okay, so we have U is equal to well, yeah, I guess we can just write that. Okay, again, I'm just rewriting U. I'm going to rewrite A. And I'm rewriting B. Okay. Okay, so I've never done this, so hopefully this works. Nice, that's what I wanted. I want to be able to cross out um, my sets without having to rewrite them. Perfect. So let's officially begin here. So A, we want to find A union B. We want to find the complement of A union with B. Okay, so first of all, what we have to do, as mentioned, is we have to find what the union of A and B are. Okay, because again, we have to do what's in the parentheses first. One moment. Okay, sorry about that. So let's find what the union is. So the union is going to be everything that's in A and everything that's in B. Okay, so, well, no, now that I think about it, I didn't really think about it, did I? Okay, so we'll write A union B. So A union B is going to be A union with B is going to be the set 1, 3, 7, 8, 9, 10. 7, 8, 9, 10. That is A union with B. Next, we're going to find the complement. Okay, so if A union B is everything written in yellow, I had to find the complement of it. So we're going to cross out what is not in the A union B and what is in the universal set. So 1 is in both, 3 is in both, 7 is in both, 8 is in both, 9 is in both, and 10 is in both. So what remains in my universal set is 2, 4, 5, and 6. All right, so 2, 4, 5, and 6 will be my my complement. So, and I guess we'll put it down here. A union with B and the complement of that set. And of course, let's see, we those that are watching the Zoom meeting, all these toolbars in the way. But if you watch this on YouTube, the toolbars will not be in the way. But 2, 4, 5, and 6 are in A union B, the complement of A union B. Sorry, the complement of A union B. All right. So let's do B. Let's do. Hopefully, I wonder if I can. Can I paste? Oh no, I can't. Shoot. I'm gonna have to write all that again, aren't I? Okay. Well, that good idea didn't last too long. Okay. So next we're gonna find the for B, we're finding A complement intersected with B complement. Okay, well let's go ahead and write what's A complement. So A complement is going to be those elements that are in those elements that are not in A. I'm sorry, that are not in A. So let's make this a little bit larger. We'll do this the other way I was thinking about, which turns out might be the smarter way. Okay, so A contains 1, so we cross out 1, 3, cross out 3, 7, cross out 7, 9, cross out 9. So A complement is going to be all those elements that are remaining, so it's going to be 2, 4, 5, 6, 8, and 10. That's A complement. Now let's find B complement. B complement is going to be those elements that are in set that are in the universal set that are not in B. So we cross those out. So 3 Cross those out. 7, 8, and 10. So my elements are 1, 2, 4, 5, 6, and 9. Okay, so I found the complements of A and B. Next, what I need to do is I need to find the intersection. And if you recall, the intersection are all those that all those elements that are in common with both the sets. So I want to find what is um, the common elements of this. So we'll write this as A complement intersected with B complement. That is going to be equal to the set. Okay, so it looks like 2 is in both sets, so 2. Looks like 4 is in both sets, so 4. 5 and 6 are in both sets. 5, 6, and I believe that's it. 8, 9, 10. So yeah, 2, 4, 5, 6. Those are the only elements that are in both A complement and B complement. And I think that's a pretty good example of complements. All right. Think. Yeah, cardinal number. Okay. So example 7. We're going to find we're going to find. I guess even more stuff. So let's go ahead and punch through this. Seems like a lot. Alrighty, so A reads, the problem reads, the Venn diagram figure 17 percolates with interesting numbers. Use a diagram to determine each of the following sets. So A union with B. So it's going to be all the elements that are in A and all of the elements that are in B. Okay, so it honestly looks like it's everything but the number 666, right? And again, it's showing the different areas 1, 2, 3, and 4. Okay, don't get caught up on that. And again, for this lecture, I mean, obviously in the textbook, you will have the values 1, 2, 3, and 4 on your text, but for the video lecture, just so we don't get confused, because I mean 1, 2, 3, and 4, those are numbers, right? Not interesting numbers, but they're numbers. We're just going to go ahead and mark those out, just kind of get rid of them. So what is an A union B? Well, it looks like A union B is going to be the set. It's going to be a set. It looks like pi e the square root of 2, the square root of -1, e to the I pi, or pi I in this text, pi I 10 to the 100th, and our aleph null. Oh shoot. Well, we're out of room, but hopefully you get the idea there. We'll go ahead and put that on there. All right. B is going to be the A union with B. We're going to look for the complement of A union with B. Okay, so if A union with B was everything that we just wrote up here, okay, well, the complement, if you recall, is going to be what is not in A union with B. Well, as we mentioned on accident, we said earlier, we said it's everything, A union with B was everything but 666. Well, the complement of A union with B is going to be simply 666. C, A intersect B, well, that's easy. It's nice and laid out for us. It's going to be the dark blue area there. So it's going to be the square root of 2 and the square root of -1. Oh, and the square root of -1. D, A intersect would be complement. Okay, so A intersection A intersected with B, we said was in that dark shaded area. Well, the complement of that is going to be everything but that. So it's going to be all this, and 666. So it's going to be everything but basically what we wrote in C. Everything but that. So it's going to be pi e to the pi I there, 10 to the 100, 2 to the aleph null there, and 666. Sometimes when I make curly braces a lot, my curly braces end up looking pretty bad. All right, and let's put E in yellow, kind of to differentiate the different colors there, so I don't run them together. So E is the A complement intersected with B. Okay, so now we're getting a little tricky here. A complement intersected with B. So what is in the A complement? Okay, well A complement is going to be, I guess what in blue. A complement is going to be all of, okay, hopefully you can see this. Okay, so I don't know if you can tell, but over I'm going to be drawing over in on the circle here. So the A complement is all this. Okay, well we're looking for A complement intersected with, oh I'm sorry, not even all that. It's this, just simply this, because I accidentally circled the intersection, but those are in A, aren't they? So that is obviously not A complement. A complement are just those elements that are in B, as well as 666. So A complement intersect with B, well, it looks like it's just going to be everything that I circled there in the blue except for 666. So, oh yeah, keep forgetting to write my curly brace there. After I draw so many of those curly braces, it just kind of gets, I get lazy with it. 10 to the 100, and then 2, right. And then F, please don't be long. A union with B complement. Okay, so this that's not terrible. So let's go ahead and look at B complement. So what is in B complement? Well, the complement is going to be all those values that are not in B. And the elements that are not in B are going to be pi and E. So, well, sorry, pi E and the square root of 2. So we're going to say we're going to say the union of A with the complement of B. Well, A by itself already contains pi E, the square root of 2, and the square root of negative 1. Even though those elements are not in B complement, they are in A, so we have got to include them. Okay, so all the elements that are in A, and then of course the elements that are in B complement will be 666, and that's it. Okay, again, pi and E are in B complement, and so 666, and then we union that with A, which was these first four terms here. So this one was kind of tricky because we still include the square root of 2 and the square root of negative 1 because they are in A. And yes. Mm-hmm. Okay, so for E, it is A complement intersected with B. So let's concentrate on that with its own page, just so I can really drive the point home instead of working with that small little picture. Oh, that's not what I wanted. Okay, so E is what we're really focusing on here. So let's first look at A complement. A complement, again, are the elements that are not in A. So I guess we'll just go and blow this up. Alrighty, so what are the elements that are not in A? Well, it looks like e to the I pi, looks like all these are not in A, right? So if you, again, recall, this whole circle here is A. The A contains four elements, pi, e, the square root of 2, and the square root of negative 1. So I complement are the sets, I'm sorry, are the elements e to the pi I 10 to the 100, 2 to the n0, and 666. Okay, and again, just, we ran out of room, whatever. All right, that's A complement, right? And B, what are the elements in B? Well, the elements in B are the square root of 2, the square root of negative 1, e to the pi I, 10 to the 100, and all right, first aleph null. Okay, so I wrote the elements that are in A complement and B. E is wanting the intersection of them. So we're wanting to find what is in both A complement and B. So what is in both of them? Well, it appears that e to the pi I is in both of them, 10 to the 100 is in both of them, and our first aleph null is in both of them. And that is how we get e to the pi I, 10 to the 100, and our first aleph null. That is how we got the intersection. Pretty sure that's what we said. E to the pi, yeah. Okay. All right, last concept. Last concept today, we're going to be talking about the cardinality. All right, the cardinal number of the union of two finite sets. All right. Dadgummit. And we'll snip this and put that on there because this is a continuation of basically the whole blood drive thing that this section is talking about. I'm not going to necessarily go over it 100%, but I will talk about the cardinality of the union of two finite sets. So starting from the top, the cardinal number of the union of two finite sets. If you recall, the cardinal numbers that we talked about before, and when we talked about the cardinality of a set, are the number of elements in the set. This is no different. It's just now we're going to be talking about the union of these sets, right? So if you recall, we put in front of our set on the previous section to denote our cardinality. Well, and again, this makes sense logically if you just stop to think about it. The formula for the cardinal number of the union of two finite sets. So the cardinal number of A union with B, okay, which if you have a certain amount of elements in set A and a certain amount of elements in set B, well, the union of both of them is going to be every single element, right? And that's where we get the first part of the cardinality, right here. Okay, you just basically add everything up, and that makes sense. Well, after that, you have to subtract the intersection of those because, well, otherwise you're going to be counting twice, right? And in this particular, well, I just don't feel like example. It's a really good example to drive the cardinality of these of the union of sets home, but it's there. But again, if you think about it logically, it does make sense. We want to add how many is in both sets, and then subtract the intersection of both sets because we don't want to double count. Right? And again, example 8, it's presented to you. Read the textbook. It's very helpful as we go along with our blood drive. Again, my best and worst professor I ever had taught me to read my textbook, and I got really good at chemistry. So hopefully you can do the same. But anyways, that does conclude today's lecture.